The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
In the year 2000, Ben Heckendorn built his first mod.
We can rebuild it. Smaller, better, portable.
Since then, he has continued his work, helping those in need with creative new projects. If you've got an idea you'd like to see built, why not send it to the Ben Heck Show?
Hello and welcome back to the Ben Heck Show. In today's episode, we're going to be building an automatic houseplant rotator. David, a viewer in Kansas, challenged me to tackle this project, and I'm going to tackle it. Let's see what I can come up with. So the plant rotator. The theory behind the plant rotator is that if you just let your plants sit in the window, they'll grow a lot on one side and not on the other, kind of like mutants. So the optimal thing to do is to rotate them 90 degrees per week, or about 12 degrees a day. It's actually probably more like 11.5 degrees per day, but whatever. So 12 degrees a day. So how are we going to do that? Originally, the suggestion was to use solar power. I was playing around with some cells, but I didn't have quite enough. I'd need a lot more power than the batteries would be in order to charge the batteries. So I decided to just go with a wall wart because I have a bunch laying around and I need to use them up. So after that comes the timing. We could either use the classic 555 or a microcontroller. 555 is cheaper, sort of. Microcontroller is much easier. I'm kind of lazy, so I decided to use a microcontroller. So today we're going to use the AVR Tiny 45, which is a really, well, tiny microcontroller, but it's kind of neat and it's cheap too. You could spend like 25 cents on a 555 or 75 cents on a AT Tiny. So for only 3 times the cost, it's much easier to use. Of course, in a large volume, you probably wouldn't do that, but I don't know, it's just a lot easier to use microcontrollers these days. So after that comes the actuation. To rotate our plant, we need to have a way to do it. So I'm thinking what we'll do is we'll use one of my surplus DC gear motors, which is a DC motor with a planetary gearbox on it, which gives you a lot of torque at the shaft. And then the top-down view, we'll have our DC motor here with a gear, and it'll actuate an inner gear here to rotate our entire plant. That should give us probably around 10 pounds of movable force. That should be enough. So once per day, it'll go just to rotate 12 degrees. So we're basically building a computerized, mechanized, lazy Susan. So we have one of these gear motors left over. I always buy them in pairs at surplus stores. We use the other one on the camping episode for the solar-powered rotisserie. Anyway, so I'm just going to double check the drawings I already have of this motor, make sure it's okay, and then I can use it to design the gearing for the flower pot. There'll be a big gear under the pot and a smaller gear here, so it reduces the speed and increases torque, because we don't have to rotate it fast, but the pot's kind of heavy, so we're going to need torque to rotate it at all. So here's a useful program I found off the internet called Gear Generator, and I can use it to, get this, generate gears. So we're going to want to create quite a gear ratio on this, probably at least 4 to 1. So the motor won't move very much at all, but that's okay because we needed torque instead of speed. Then what we'll have to do is we'll have to figure out, you know, the gear ratio versus how much we want the pot to move, which is 12 degrees per day, and then divide that by the circumference and math and blah, blah, blah. We'll figure that out later.
Using my laser cutter, I made a set of gears to rest the plant on. Next came the legs, which space out the area needed for the motor, and have bearings on the ends of them for smooth movement. Then I installed the gear motor, which apparently cost $14.50, and then connected the 2 halves together. Now it's ready to go.
The plant's gonna get dizzy. We've got the assembly put together, so now we're going to simulate a plant being on it. I don't have very many plants at my shop, but this should do it. We'll try full rotation and we'll also try 12 degrees. Okay, I'm going to set these screws together. What you do is you basically twist the screws into each other. That way they won't move on the shaft since they're locked to each other. We're going to do the circuitry next. Before I do that, I'm going to make a simple power supply. We have an old AC power cord. I'm going to hook it up to this 5-volt power supply I got from Halted Electronics. So we'll just strip off this, and then we have, of course, ground, neutral, and live. We'll hook up here, and then we'll be ready with that, and then we'll move on to the electronic stage. All right, we have live and neutral hooked up from our AC cord. We still have ground open. Now, not everything uses ground. This little adapter didn't use ground, for instance. Usually, objects are grounded if there's bare metal someplace on the object that the user can touch. So a plastic little power supply isn't going to have it, but a power drill might if it has a ground surface. So what we're just going to do, just to be safe, is we'll take the ground, which in this case it actually means earth ground, and we'll hook it up to the negative part of our DC output, just to do it the proper way. Usually if you have like a computer or a large piece of electronics, all the RF shielding in the device will be connected to earth ground, which is green on an AC line. All right, now it's time to make the device move on its own. So I've got two integrated circuits here. This is the classic 555 timer circuit. We've used it a couple times in the past. You can do a lot of things with this, but I'm feeling kind of lazy, so I'm thinking about using this. It looks the same, you might think, right? Well, it isn't. This is an AT Tiny 45. It's a microcontroller. Now, the reason I think I might use it is, well, besides laziness, you're talking about like 25 cents for this, you know, just integrated circuit. A microcontroller, you can get these for like 75 cents from Newark Element 14. So why not just use a microcontroller? Granted, if you're doing this in large scale, you might want the absolute cheapest solution, but I don't. So I made my little AVR programming board here. See, I can put in the larger one as well as the small one. So I'm going to plug the chip in. This is the AVR ISP Mark II. It's basically an SPI, or serial peripheral interface programming device, and it plugs in right here. All right. So what we're going to do with our program is we're just going to make it once per day pulse the motor for about half a second. So to simulate that pulse, we're just going to hook up an LED, which will show us that it is doing the pulsing. This LED represents the MOSFET we're going to eventually put in. One trick that I've come across, which is easy to forget with this, is you have to power the programmer with a USB cable, and then the AVR you're trying to program, that needs to be powered as well. Okay, now we're going to use AVR Studio to program this thing. I have AVR Studio 5.1 on this computer, but there's newer versions. I think they're up to 6 now. So first I'm going to go up to Tools and AVR Programming. Then I'm going to select my tool, which is the AVR ISP Mark II Programmer. The device, I have an AT Tiny 45. Interface, that's correct, hit Apply. Now if I hit Read, I should be able to see my device ID, which means it's working. All right, so here in our program, we want to define the frequency of the CPU of 1 million, 1 megahertz. We need to include the AVR input-output library and also the delay library. Now we just made a few simple things here. We have pin set, and remember when you're programming an AVR itself, unlike an Arduino, you actually have to do the low-level pin function. So you don't just say pin digital write 1, 0. You actually have to use the ports. In this case we're using DDR-B, which is the direction port B. So when you set a pin, you want to make sure it's 0 or 1. 1 is output, 0 is input. So we have to set the DDR-B for the input-output of the pin. Then to actually set the pin itself, we use port B. So DDR is direction of port B, and port B is what the pin actually is. All right, now here's our main loop. We have pin set 4, 1, which means take pin 4 and make it high. Wait 1 second, then make it low, then wait 9 seconds. Now I was just using this to test the frequency to make sure it was okay, and it's pretty close. So what we're going to want to actually do is wait 86,400 seconds, which would be 1 day. So once a day, it'll do a pulse to move it. Maybe it's not the most efficient thing, but you know, it seems like the easiest way to make this work. All right, so I've got the code here. So it's going to pulse that pin high for half a second, then make it low. Then it's going to repeat a loop where it counts up 8,640 seconds 10 times. The reason I'm doing that is because this is an 8-bit processor and we don't want to use any numbers that are too large for it to process. But in the interest of being able to see it actually do something, I'm going to just have it wait 1 second 10 times so we can actually see it move, because we don't want to film it for a day. That would be the world's most boring time lapse. And then once we have the code ready, we just go up to build solution, and it will send it right to our chip. Okay, I've got it reset. So it'll go for half a second. Then I'm just going to have it wait 10 seconds, and then it'll do it again. So we could put some other functionality into this. We could have like a light timer, you know, other sort of functionalities. But I'm basically just using this because I'm really lazy. Now that you've seen us program the AT-Tiny, we're going to talk about how to connect it for our use. So here is the integrated circuit here. You don't need a whole lot of connections for it. You put your positive voltage here. We're using 5 volts in this case. The ground is down here. And the remaining pins are your ports, your general purpose input-output. One of them is reset. You can actually use it as an I/O, but if you do, you won't be able to reprogram it. You'll have to use a high voltage programmer. So we're just gonna use this as reset and pull it up high using a 10K resistor so it won't reset. So over here, we have our speed selector. So we use 2 pull-ups on the first 2 pins of the port to pull them high, so they'll normally be 1. And if you click the switch, which in our case is gonna be a dip switch, you can send either one of them to ground, which sets the speed as fast or slow. So the input pattern in memory will be 0, 1 or 1, 0. So, and then the output signal that actually tells the motor to move, you know, once a day about 12 degrees. We pulse this line here. We have a pull down resistor, which means if it's left floating, it will not trigger the MOSFET. It'll be a 0. It's always good to have pull downs and pull ups because you don't always know what state your lines are going to be in, so you ensure that they're in a certain state by using pull ups and pull downs. So we go over here, we have a MOSFET, and so we have the positive voltage coming into the MOSFET, and when the gate is triggered by this line, it allows the current to sync through the motor to ground, causing the motor to activate. So we're going to do up a little breadboard that has this circuit on it, and we will go from there. Inserting the embedded processor. Here's a PCB version of what we drew on the whiteboard. Got your AT-Tiny here. We've got some pull down resistors here. Pull up resistor for reset, so you can have the reset button. Here's our MOSFET, which actually powers the motor. Here's a capacitor. This allows the motor and the processor to work together without losing power. There's a little slide switch here, so you can select fast and slow. So fast, it's going to rotate. Well, right now it's rotating fast just so we can see it, but it'll rotate once per day or once every minute. Those are going to be the 2 settings. Now that we have the gizmo working, we can test it out using a real plant and some real sunlight. So there you have it, a plant that automatically rotates once a day, 12 degrees. Right now we have it sped up so it rotates every 10 seconds just so you can see it working. But you know, there's a switch here where you would say, okay, once every minute or once every day. So right now I have it set at the fast setting, which is just once every 10 seconds. So there you have it, using simple electronics to solve an everyday problem that I didn't even know existed, but I guess it does. Plants need to be sunned evenly. That's all the time we have for today. In our next episode, we're going to be building automatic sunglasses. We'll see you then.